All right. Hello and welcome to Meeting C++ with this real great new tool for hosting this virtual conference, providing a way to still get together like in-person events, which we hopefully will have maybe next year. I'm Andreas Fertig. I work as a trainer and consultant for C++. I'm also obviously a speaker and the creator of C++ Insights, a tool which sadly we will not use today, but we will see Compiler Explorer. The topic of today is C++ 20's templates, the next level concepts and more. So we will look at what C++ 20 brings us to make templates, well, usable in a wider range for people, and hopefully scare less people away. Yeah, that's interesting because Meeting C++ would be hosted in Berlin usually, so that's Germany, and I'm German, and this is my last name. My last name is obviously German. It's pronounced Fertig, and you can translate it to finished, ready, complete, or completed. It's a really nice name if you look at it that way. In German, the issue is, as a last name, it's spelled with a capital first letter, while as an adjective, it's spelled with a lower first letter. So I have a constant fighting with my spell checker. And I like to say I think I'm really good with C++ in general. And despite that I'm German and my last name is Fertig, which is a very common word in German, it took me quite a while, 30 years roughly, to learn that I mispronounce my own last name. In proper German, it's Fertig, with he at the end. But as I said, I think I'm much better in explaining C++ and using C++. So let's switch to that. Concepts. Concepts allow us to formulate requirements for a type. If you want, and if it's easier for you in the beginning, you can compare it to a std enable if. But a std enable if is only a teeny tiny portion of what concepts can do for us, okay? But if it helps your model, let's start with this one. Concepts always consist of the definition of a concept, which we have a new keyword for to define that, that's concept, and requirements. Concepts consists of a couple of requirements, at least one or more, and to specifying those, we have another new keyword called requires. Okay, in the figure below, you can see how we can compose a concept. It always starts with a template head because concepts are meant for generic code. They are always templates, so they start with a template head. And in the template head, we can use all the usual things we know from functions or function or class templates. We can use type and non-type template parameters. We can use variety arguments. We can use only a single type named T. We can use multiples. We can go crazy with class and type name and figure out the tiny differences and when they matter between the two. But that's the template here. That's the usual thing you already know. And in the next line, we have the new keyword concept. That's where we see, and the compiler as well, that we are starting to define a concept here. And followed by the keyword comes the concept name. You can use any usual variable name or any syntax to declare variable names. They are applicable here as well. I chose my concept. It's really bright concept, I know. And then after the equal sign, we assign requirements to this concept. In this specific case, 3 of them stood same as. That's the first concept you see. Figures out whether 2 types are the same. And then is class V and is enum V. And as you can also see, we can use Boolean algebra to piece them together using and or. Okay, so that's how a concept itself looks like. Now let's explore how they help us and then where to use them. Let's say we want to write this function add. And this function add, it should use a vertical amount of parameters. So x and epsilon here in the code listing illustrates and should be usable with 2 and with 4 parameters, and of course more and so forth. Okay, you get the picture. The only thing for now I want to restrict is mixed types. This is line number 3, where I call add with 2, 3, 3.14. This is something I like to forbid at this point, because implicit conversions are fine, but implicit integer conversions are, if they are narrowing, it's not that great. Okay, so that's the task. And we can easily see, okay, that should be a veridic template at this point. So let's see how we can compose that in C++ 17, okay, with the restriction. Pardon me, I forgot one thing initially. I ask you to hold your questions to the end of the talk. We either have a couple of minutes there to answer them, or Jens arranged one of these extra rooms where we can all come together after the talk and discuss your questions. Okay, I have roughly 10 minutes to discuss them. After that, I have to switch to the book fair to present my C++ 20 book, Programming with C++ 20, which I welcome you to join as well. But back to our example here. So how to implement this function add in C++ 17. This is my approach. The grayed out code, that's not the important one here. I quickly walk you through. It's just two helpers. The first one is our same v. It's in line number 2. It's a variable template from C++ 14. And it uses std conjunction v and std same as to look, to compare our type name t to all the arguments in a parameter pack. So std as same compares t against every element in the parameter pack, and std conjunction ends them together, seeing whether really all of these is same calls will return true. So this is our check to ensure that all parameters in a parameter pack are of the same type. And then below in line number 10, I have another helper, first arg t, and it's supposed to grab me out the first argument in the parameter pack, because all arguments should be of the same type. Whether I pick the first one or the last one or some type in the middle doesn't matter. They're all the same, so I'm picking the first one out here. And now to the code at the bottom. That's the implementation of add. We can see in line number 1, yes, it's a variable template. It starts with type name ... So obviously there's a parameter pack. And then in line number 3, I see the function name. It's called add. I'm passing the arguments to add and expanding the pack here, or the pack itself. And in line number 5, I'm using a default expression from C++ 17, expanding all the arguments in the pack and using the plus operation to add them together. Okay, so that's so far all right, especially with C++ 17. That's, I think, really nice code. The issue I have, and that's the line I skipped intentionally, that's line number 2. And I wrote this piece of code. Okay, so that's my own code I'm judging here. It's the std enable if t. It's the best enable if you can get, because it's the enable if t, which already spares you typing type name in front of enable if. Well, that's great. But other than that, we are looking at a really bizarre looking construct here, especially for people who don't write template code every day or who are new to C++. We have to know that the first thing we are passing in our same v, that's a Boolean condition. So our same v returns true or false, and depending on this being true, first arg t, the second parameter to enable if, is what enable if t returns me. And that's also the return type of add, because you don't see that anywhere else. This is in the enable if. And if the enable if, or the our same v better, yields false, then the entire enable if cannot be instantiated. We're talking about spin here. And this add function, well, never makes it into the binary, probably you're looking at one of these page-long error messages where the compiler tells you all the combinations it tried to instantiate a variation of add. So I prefer putting the enable if at the return type because there's a place where nobody else can tamper with. All other things like default parameters, the people can modify it. So this is the best way, I think. But it's still hard to read, it's hard to teach. There's a lot we have to know about this, and the return type is obfuscated. So it's misusing that thing. And what does enable if mean anyway? And then it enables or disables something, I don't know. So this here is the C++20 version. In all fairness, it also requires the helper rsamv, which I omitted because it's the same as we saw on the previous slide. In line number 1, we still see varied template. There's the familiar template head. Line number 4 now starts making more fun because there I see auto as the return type of add, and the rest of add here is the same, the signature. In line number 6, I see the fold expression as before, expanding the arguments in the pack and using the plus operation to add them all together. So line 4 is already an improvement. I have my return type back, but why? The why is in line number 3. Here we are looking at another part of concept, the requires clause, which is one of the fundamental building blocks for concepts. So in line number 3, I'm now saying requires rsamv of my parameter pack args. That's a really good and precise description, right? This add function requires that rsamv is true. I accept that we might have to look up what rsamv is and what it does, but the rest of it, it's so much cleaner and clear what it does, and no more tampering with return types, which was wrong all the time, but the only way how we could achieve what we wanted. So this is the first thing what C++20's concepts give us, where we look at a really simple example already, okay? And that's not concepts, just a part of concepts. That's the requires clause, okay? Now, here are the different application areas for concepts. We can use them as illustrated in C1 in the template head as a type constraint. And there they replace the type name or class. So upfront, we can start being very specific and say in our template head what subset or what constraint type this template at this point requires. Okay, we don't have to go down. There is no static assert that way too late tells us, well, the type is, it's not really wanted here. We can say this initially. That helps a lot because it's also documentation. The other place is the one we already saw, that's C2 in the so-called requires clause. Okay, in C1 we can only use concepts. In C2 we can also use type traits, for example, and we can use Boolean algebra to say C2 and some other requirement and some other requirement and so forth. In C3 and C4, we're looking at so-called constraint placeholder types. These are more or less types where we have auto. And C3, you already know that's the return type of the function, which can be auto. You can also see this, it's the same for auto variables, so for placeholder type variables, where we can say auto. We can put a concept in front of them to constrain these types. So we can here, in this case, constrain our return type. We can also constrain variables that are of type auto. And in C4, we are seeing something slightly new. You might already notice from C++14's generic lambdas. There we could already have auto as a parameter type. And this was extended, and we are looking at abbreviated function templates here, which we will see an example about later. But from syntax point, it's the same as for the return type or for auto variables. We can now say auto is a parameter type, and we can constrain that with a concept in this case. The same goes for C3. All the concepts are allowed in these places. And then in C5, we have the so-called trailing requires clause. That's more or less the same as the requires clause in C2. We can use concepts and type traits here. And the trailing requires clause is very neat if we need to constrain a function that's not a template, but maybe inside a class template. So a method inside a class template, we can constrain with a trailing requires clause. So application areas for concepts. Let's circle back to our add example, and let's look at it with some fresh eyes. Currently, add only prevents mixed types. So I can only stick in types of the same type, which is reasonable. But the current add version leaves a couple of things unspecified. So currently, in my implementation, I can call add with only one parameter, or technically only also with 0 parameters. And that makes absolutely no sense. Maybe in highly generic code, yes, granted, but let's say we want to prevent this. The function's name is add, so it's supposed to add at least 2 things together. Calling it with 0 or 1 parameter, that's just a waste of resources. So let's not do that. Let's limit add here as well. Then a possible requirement C in the next line is the type used in args must support a plus operation. You might not even have thought about this because I showed you the implementation, but that's a design choice. I could also have required that my type must provide a member function add, or that there should be a global function subtract, which I call, which makes even less sense, but it's possible. Okay, plus is reasonable here, but it's hidden inside of the implementation, and we have to figure that out once we pass in a type that doesn't meet this requirement. So that's one of these implicit arguments. And then we have D, the operation plus should be no except. Add itself is no except. I'm not sure if you spotted that one. So let's make the plus operation, or ensure that the plus operation is no except as well. I don't want to build a try-catch block around this thing. And the last one, E, is an interesting one. The return type of the operation plus should match the one of args, right? So usually our operator plus, if we implement it, it returns the same type as it's called with, so usually the class. But it doesn't have to. It doesn't have to. So to avoid surprises here, let's require that the operation plus should return the same type, or must return the same type, okay? So these are 4 additional requirements that are pre to C++20, not that easy to implement. So let's see how we can do in C++20. And for that, we need another new thing, and that's the requires expression. We will see a lot of requires in C++20 code when it comes to concepts. The graphic here illustrates how this thing works. So I read it like a function that's always called requires. It doesn't have a return type, so maybe a constructor or something like that. And it comes with a parameter list. And in this parameter list, I can declare any kind of parameter I want. I can use all the types that are already available, like built-in types, like types from headers I included previously, say std string, something like that. I can use const and ref and star here, so I can use a const t ref t, for example. You can go crazy with left and or east and west const. Everything is possible here. The requires expression is only used at compile time to evaluate whether the requirements in its body are fulfilled. Okay, it never goes to your binary, so we can also use my t and u here are template parameters. They are coming either from the concept or from the template this requires expression is used in, okay? So that's why you can make up any type combination here. It's just to use them later, and we will see an example where it's really handy and helpful. And the requires expression now itself comes with one requirement. Its body must have at least one requirement. It can have multiple, but it must have at least one to be valid. So here we are looking at a requires expression. Previously, we already saw a requires clause. This was on C3 and C4 on my application areas of concepts overview slide. And we can see a requires clause as a Boolean expression. And the requires expression, well, that's a little bit more complicated. It's like what we have with no except, where we can ask a function whether it's no except or not, and we can mark a function as no except. So here we can see the requires clause we previously saw, like an if, that evaluates a Boolean expression, and our requires expression, which we are looking at here, provides such a Boolean value. Okay, so this is how you can distinguish these two. Now, in this requires expression, we can use 4 different kinds of requirements. We can use a simple requirement, a nested requirement, a compound requirement, and a type requirement. The last one doesn't make sense for this example, so I will show you an example about this later. And let's start simple with a simple requirement. A simple requirement checks whether an expression is valid and will compile. That's all it does. So here in line number 1, I'm starting my requires expression. I'm using the parameter pack args. And in line number 3, I'm formulating the simple requirement by reproducing the fold expression I use in the function's body. That's a repetition I dislike, but that's mostly subject to the example I chose here. So that's all. What a compiler does for a simple requirement is it checks whether it's instantiable. Okay, so it, for example, would detect here if my type would not provide an operator plus, but it would also detect other things. So what we now limited, or what this requirement checks here, is our requirement C, that it no longer works with a struct called noAdd, which obviously brings no operator plus. And if I now call add with 2 noAdd instances, then this requirement will yield false and will most likely abort the compile with that. The next thing is the nested requirement. A nested requirement is a little bit tricky at this point. What it does is it evaluates the Boolean return value of an expression. And in line number 4 and 5, we see a nested requirement. And it always starts with requires, so the next requires. And this requires here is really important. If you focus on line number 5, and if you omit the requires, then you have only size of ... args greater 1. And this size of ... thing, that's an expression, and without the requires, this is a simple requirement, and the compiler will only check whether it's instantiable, which it will always be, even if there are 0 arguments in the pack. So we need the requires in front of it to force the compiler not only check whether it's instantiable, but also evaluate it at compile time and give us the true or false condition. Okay, so this is the same for our same we. We have to put a requires in front of it. And with that, we have our next 2 requirements, A and B, checked. And below in the code example, you can now see that I no longer can call add with 2 and no add, and also no longer can call add with only a single parameter. The requires expression, as we see it now, limits the 3 requirements we found earlier. So the last one we have to check is the compound requirement. And the compound requirement checks 2 things at once. It checks, or it can check, whether the expression was no except and the return type of this expression. So in line number 10, you see these 2 checks in one line. It starts with the curly braces, and then sadly I have to repeat my fold expression. As I said probably due to my example. And then I say no except. And that tells the compiler, instantiate, and at compile time, look at these expression in the curly braces and figure out whether it's entirely no except or not. If the answer is no, this requirement yields false. And then there comes the thing that looks like a trailing return type error here after the no except, and it points to same as. And same as is a concept. It is a place where we must use a concept. Same as comes with ++20, and it basically checks whether two types are the same. Okay? And you can see I'm using first RT here, so my helper grabbing the first type of a parameter pack, and yeah, well, to what do I compare it, right? Same as should compare it to something. What a compiler does here, it figures out the type from the compound requirement. So from my expression at the start of line number 10, grabs the type and puts it as the first type in same as. So it puts that type implicitly in there, and by that I have the two types. So the same as here compares the resulting type of the plus operation to my first argt. And with that, we have our last requirement checked, or our last two requirements, D and E. I can no longer call add with a type that has a throwing operator plus, and I can no longer call it with one that returns a different type in its operator plus. Okay. Practically, you can split these two checks into two lines of code. That's line number 8 and 9. That's totally valid. I simply prefer to have them in one line to reduce repetition at this point. So congrats, we have checked all our requirements. We found all the implicit ones in add. So let's put it together. Here is what's called an ad hoc constraint. In line number 1, we see a template head. In line number 2, we first see a requires. This starts the requires clause, and then the gray part, that's the requires expression we just did build together. And then line number 9 and 12, that's our implementation of add as it was before. Okay, there's nothing new going on. Line number 2 is the interesting one. There we say requires. Whenever you see that, you know two things. First, we are looking at an ad hoc constraint because we say requires. And second, that's potentially the first sign of a code smell. Why? Because we just spent a couple of minutes creating this requires expression. Okay, and it has 4 lines of code for a very simple thing at this point already. So these things tend to grow. If we can limit our types, if we can constrain the operation, if we can be more precise, then we should do this. And that means that we potentially write more code to specify the constraints. But now we placed it, or we put it in one place. And if we need it in another one, copy and paste is not the best option at this point. Okay, this is why it's the first sign of a code smell. For the add example here, maybe we can say it's so highly special and specific, it would be okay. Okay, it's always a design decision, but it's a first sign of a code smell, so think hard about this. The alternative, which I prefer in this case even, is creating a concept. So this is our first own concept. It starts in line number 1 with a template head. It takes a varied number of arguments. In line number 2, I say it's a concept. I call it addable. And then after the equal sign, I assign the requires expression we previously created and used in the ad hoc constraint as well to assign it to this concept. And then in line number 10, we see the add function again. And in line number 11, I would say it's now even easier to read. I say requires, so that's the requires clause, and then I apply the concept to it, addable. Okay, so for me, the function is here very clear to read, so I think that's nice. But it's also more reusable because now I have a concept that I can use in different places. Okay. Because we will use concepts more and more, and they will start becoming more important and more complicated, it's important to test them. And here's one approach that you can do. I have in line number 3 this class template called stub, which takes 3 non-type template parameters to control whether the operator plus is no except, whether it has the operator plus at all, and whether it's the correct return type that this operator plus returns. Okay, this is what we have here. And I use this stub then in line number 16 to 19 to create nice aliases like no-add and valid class, because I always fail to remember what stub true, false, true was doing. So it's no-add. And with that, I have everything in place to simulate the different conditions I can feed to add. And now the best thing is we have everything other in place as well. We don't need to go out and find a cool testing framework. We already have it. It's our compiler, and it's called static assert in this case, because concepts are compile time predicates. So we can use that in a static assert and test it at compile time. As I do here on line number 2, where I test that I cannot call addable with int and double, and so forth. Then in line number 10, for example, I use the stub with no add to check that I cannot call addable with 2 instances of no add and so forth. So this is another way where concepts are a little bit better than ad hoc constraints, because I can now test them without having to test a function. But you may also want to add tests where you test the requirements for the function as well. But now you can see if just your concept fails and the implementation of the function has a different issue. So this is how you can test concepts. It's built in, use it. It's really cool. I promised you that we also talk about abbreviated function templates, and this here is my motivating example. I do have this function template called doLogged, and this is a pattern I use very regularly, where in the body of this function template I acquire a log, or maybe I do something else, but in this case I acquire a log, and once that's achieved in line number 6, I'm calling the function f. Okay, that's all that thing does, but it spares so much code application all over the code base and gives so much more control. It's really worth it. But there are 2 things that bother me. Line number 1, the template head. It has as many characters as the entire declaration of doLogged. And the next thing is, look at f. It's a template parameter. Nobody knows what it's supposed to do. In line number 6, you can see that it must be some callable, some function pointer, something that's invocable. But that's not obvious if you simply look at the signature of doLogged. Can also pass an int in it to it, and then you're back in the error world. Okay, so that's not great. In C++20, I can solve both the issues I have with the previous code with abbreviated function templates. The first thing is I can get rid of the template head in total because I use auto as a parameter, as you can see in line number 1, and then I can use auto together with a type constraint. Std invocable is a concept that's shipped with C++20, and that signals that you should pass in something there that's invocable. So you can see it by looking at the signature. You don't have to go down in the function's body. It's documentation, and it's checked by the compiler, okay? And no comment in C++17 will achieve the same thing than this solution in C++20. And of course, you can also use the template head and then put the type constraint in there, as in the figure initially presented as C1, for example. That would do the same job. One important remark is whenever you see auto as a parameter to a function, should it be a function template as here or a function as here or a lambda, then please know that you're always looking at a template. The compiler creates in the background a function template out of that thing for us. You can use C++ Insights to see it yourself and play with it. It's the same system that we already have since C++ 7, C++ 14 with generic lambdas. Okay. So how great are concepts? That's the question. And one thing that people all the time tell me is the error messages are so bad when it comes to templates. It's totally frustrating. So here we are talking about error messages. But to do that, I have this example here, and I think it's better that we start talking about something else. And that's this example. What it does is I have a, let's call it type trait is container here, that checks whether a type that's passed to it satisfies the container interface of the standard library. And the subset here is it must provide a value type, a size type, an allocator type, iterator, and const iterator type. And it also must provide the 5 member functions size, begin, end, C, and C, begin. Okay, that's roughly a container interface. And I need an awful lines of code to formulate that. And depending on your knowledge about templates or C++ in general, if you're fresh to it, that's fine. If you see this and work with this code on a daily basis, then think about how it was, whatever time it was back then when you started with C++ and templates. There are some interesting things here. Line number 2, line number 5. I have 2 times the name is container. That's really odd. Usually I get an ODR validation for that, but not here. Why? Well, we learned line number 2, that's the primary template. Line number 5, that's the specialization. All right, you can learn that. But then there's the next thing. What was std void t in line number 7 doing again? Yeah, right. Practically nothing. It's true. Oh, and then line number 12, decal type. All over the place. I'm not only talking about the repetition we have here 5 times, but also what does decal type do again? I mean, I teach it in my classes, but very briefly only because I think it's facility only, well, important for library writers. And then std decal val. Oh yeah, what was that thing doing again? Right, it creates me a type of this t such that I can call .size on it. Yeah, I can teach you that as well, but I rather don't. And then the best part is, have you ever heard about inheritance? Usually things inherit from a common base class, right? Here I have is container, line number 2, inherits from std false type. Let's ignore what std false type now is again. But line number 5, the second is container. Oh, that now inherits from a std true type. That is really odd, isn't it? It is. And then line number 21, line number 22, where I test these 2 things, I have to say : value. And where does that come from again? Oh, you say from this true type and false type thingy. Sure, I can learn of all of that. Just give me another 4 weeks or so and I try to make it. Okay, that's not nice. In fact, it makes me cry. I'm happy that we could achieve all that in the past, but you can also use a hammer to put a screw in the wall, right? So that's the wrong tool. C++ 20 is the much better tool here. First thing, only one name container in line number 2. I omitted the is, that's the common practice. Is something is for type traits, and without the is, it's a concept. So here in line number 2, I'm starting my concept, call it container, and then we see a requires expression, which takes a t, which is from the type name t. And then in line number 4 to 8, we can see a type requirement. It always starts with type name t, and it looks for a type called value type in the namespace of t in line number 4 and for all the others. And this specifically checks that there is a type behind this. That's beautiful already, right? And then line number 9, t.size. Because my requires expression provides me with a way to have a parameter of a certain type, I can now call a method on that type at compile time in the requires expression, checking whether you're looking at a simple requirement, whether it's instantiable or not. So has t a size method, a begin method, and so forth. Isn't that just nice to read? No decal type, no decal wall, no false type, no true type, no stud is void t, and all that stuff. It's gone. So much simpler. It fits in the language, and it's simple to read, it's simple to teach, and it's precise. And then line number 18 and 19, no false, no colon value. Okay, a concept yields already a Boolean value. It's already fantastic, right? It makes me really smile. But I promise talking about error messages. So let's head over to Compiler Explorer and have a look at the error messages. So this is the code from the slides. It's the same here. It doesn't mean anything if you cannot clearly read it. It's not a point. The error messages is what we are looking at. And I squeezed one additional statement in, and that's here a check for is container of std array of type int of size 5. And currently that's negated to compile. Once I remove this not, static assert fires and tells me that, well, it's not a container at this point. I think Clang is a little bit more nice here. All right, it's not the same thing. So my static assert failed due to the requirement is container colon value. I somehow guessed that, but it doesn't leave me a clue why. Okay, it's okay that we don't ship that one to the customer, but it's not helpful in finding the error. And some of you might already know what the issue at this point is. Here is the C++20 in concepts version. And now I'm removing this not from the check here again. And then we see first thing is even Clang tells us, or in Clang in C++20, your static assert failed. Okay, thanks. I expected that at this point. And then it says, because std array does not satisfy container as a node. All right. I also guessed that because that's the only thing I have in the static assert. But then the third line, that's the deal breaker. Or not a deal breaker, that's a breakthrough. Because type MT allocator type would be invalid for std array. And I also have these squiggling marks under my allocator type here. And of course, std array's purpose is to have the memory there at compile time. So no dynamic memory allocations. So yes, thank you. That's helpful. I can track that down even in a bigger code base where I don't know the types. With the error messages of concepts, I get to a point where I can fix my wrong code or invalid calls to something. So that really, really is an improvement that makes me smile. Okay, that's really, really great. So enough of concepts. Let's talk about other things that improved with templates in C++20s, namely non-type template parameters, which can now also be of type double. Here you're looking at an example where in line number 1, I can declare a template, function template called fun, which takes a double as a non-type template parameter, and that wasn't possible before. Line number 6 and 7 also illustrates that it's a very precise representation at this point. So plus 0.0 and minus 0.0 are possible, and these are different instantiations of fun. Let's look in Compiler Explorer at this once again, and this time we're focusing on the assembly output here. So this is our first call to double. And as you can see, thanks to the awesome highlighting from Compiler Explorer, this is the positive 0. And the line below, this is the call to the negative 0. And you can see that the bit pattern behind it is different because, of course, it's a different floating point number in the representation there. And once I turn off demangle identifiers, we can also see that the result is that we are getting two different identifiers for this function. So two different instantiations, which we see below. And that means it makes a difference if you're passing positive or a negative 0. It's valuable for some applications in math, but maybe a trap for others. It also increases or has the potential to increase the size of our intermediate object files because the mangled names are longer now. But as we have a lot of disk space these days, I think it's all right, and it's better to have floating point parameters as non-type template parameters than saving a few bytes of disk space at this point. Staying with non-type template parameters, what else do we have? Here we have a class template called fixedString. It takes two parameters, a type name, jar t, and a non-type template parameter size tn in line number 1. And it uses that to create an array of jar t of size n in line number 3 called data. And then in line number 5, I declare a expert constructor for fixedString, which takes a reference to an array of size n of type jar t. So the same size and type as our data member data has in line 3. And then it copies the data into its internal representation, or its internal buffer to be precise. That's cool. Now in line number 8, I can declare an object of type fixedString, call it fs, and initialize it with uniform initialization with hello, C++20 as a string. And that compiles. It's cool, right? But okay, that's CTAD enhancements at this point and not so much about non-type template parameters, but that's the building block I use in this version of the code here. Line number 1 takes a fixedString, or my class fixedString, as a non-type template parameter. So aside from floating point types, we can also use class types if they fulfill certain requirements as non-type template parameters in C++20. And here I'm creating this fixedString container class. Internally, it has a function print in line number 4, and there it counts str.data, so the non-type template parameters data member, which I made public to have it easily accessible there. In real code, you should probably think about making it private and providing a member function to access. So that's already nice, but line number 10, that's the really cool part. I can say that I'm creating a fixedString container, and then I'm using the anchor brackets, and I pass a C string to it, hello, C++. That's all. And that's the first time we can pass a string to a template as a parameter. There were only tricks before to achieve that, but now it's really possible passing it into this class fixedString, and now in line number 11, I can call fc.print, so my fixedString container object.print, and it will print out the string hello C++. Okay, so this is non-type template parameter improvements in C++20. Check them out. They enable us to write different code at this point. And of course, lambdas, who can miss lambdas in a talk? So they're in mine as well. Why? Because lambdas and templates come together. Here I have an example. It uses C++14's generic lambdas. in line number 3, I'm creating myself a variable called max, and as I assign this generic lambda to it, takes 2 parameters, x and epsilon, and internally in line number 4, it figures out which of the 2 parameters is the larger one and returns that one. Okay, it's an implementation of what you already have in the standard library, so use that version. This here is only for illustration purposes. I can use max now, like in line number 7 and 8, to call it with 2,3 and 2,3.0. I'm invoking the lambda and getting back the creator type. I'm ignoring the return value here, so it's not the most sensible code, but I'm trying to make a different point here. It compiles in line number 7 and line number 8. I don't want line number 8 to compile. We're looking at mixed types again. What's the return type of line number 8? It's a double, because that one wins at this point. But I'm risking having the wrong type here or truncating things, so I don't want line number 8 to compile. But with generic lambdas, this isn't really feasible. There are hacks to do it, and I don't want to share them now. So let's simply say it's not possible in C++ 14 or C++ 17 to achieve that with a lambda in a sensible way. C++ 20 now brought us lambdas with a template head. After the capture clause, as you can see in number 3, we can now start in the angle brackets a template head. Okay, we don't have to type is template, because that's implicit at this point then here. So we say in the angle bracket a template head. And there we can use type name, class, non-type template parameters, all what we want. And now we are looking at what we already know from function templates. I can now say that this lambda takes a type name t, and I use this t for my 2 parameters x and epsilon, forcing this lambda to be only callable if x and epsilon are both of the same type, because we are looking at templates here and there are no implicit conversions. And that means that line number 8 still compiles. 2 and 3 obviously are both integers, but line number 9 no longer compiles because we are passing in an int and a double at this point, and that does not compile. Compiler now tells me it does not know how to instantiate that lambda at this point. And that's another win. We can use now lambdas even better in generic code and also restrict them. And it's needless to say, in 3 instead of type name, of course you can use a concept there to constrain the type if you want. Okay. And just to get you into thinking about new things, here are 2 cases or 2 ways that you can now use lambda thanks to the template head. In line number 1, I'm creating myself a lambda called lamp, and it comes with a template head, type name t, and this lambda now takes a stud vector of t. Okay, that's possible the first time. So I can declare in line number 2 a variable of type stud vector of int, and I can call lamp with v, my stud vector of int, and it compiles. But I can no longer call in line number 5 lamp with the number 20, for example. Okay, because that doesn't work. And that's another thing that wasn't easily achievable before. And then non-type template parameters in the template head of lambda, that's the lower example at the bottom, line number 1 there. After the capture clause, I say size t n, and my lambda now takes a stud array of type int of size n, and n is deduced by the compiler at compile time. So in line number 3, I'm creating myself a stud array of type int of size 2, and I can call this version of lamp with my stud array, and it will work. It will stop compiling once I pass in a stud array of, for example, type char of any size. So lambdas are much closer now in the language to function templates. We can use them like we can use function templates. So that's also a great improvement here. It also removes a couple of questions I got in the past why it is not possible and that. So the syntax here is now more uniform, things coming together. All right, I hope you learned something about templates, concepts, and all the things you can now do with them in C++20. Of course, this was only a brief peek into that. There are more things that are under the surface. You can head over and subscribe to my newsletter and grab yourself a concept cheat sheet. It contains 2 pages at the moment with the most important parts about how to piece concepts together, or what's the elements in concepts and where and how to use the different things. So that's helpful. As I said, you can also later come to the book fair and check out my Programming with C++20 book, which of course also covers templates. And we now have a few minutes left. So after that, we can go to the Q&A, and if the hour is over, we can move to the table, and we have there 10 minutes, okay? So I hope you enjoyed this. I hope you enjoy C++20. I hope you enjoy meeting C++. I'm looking forward to meeting you either at Meeting C++ or hopefully at one event where we can meet in person, hopefully in 2020. At this point, I'm fertig. Thank you.
So, okay. Thanks for the nice presentation. So actually we have 2 questions here. Should I just read them, or do you want to?
If you're already prepared, it's probably, I'm trying to get to them. Okay, I see them. Okay, so yeah. First question is, as a library developer, would you rather create the, oh no, it's flipping, the egg or the chicken first? Meaning, would you rather create, for instance, a std_invoke concept first, then a std_invoke function, which first parameter is constrained using invocable, or define invocable as requires invoke? Well, good question. In my experience, these things often come together. So at the moment you start, for example, creating the function invocable or invoke, you figure out that it might be the good idea to constrain it and then write the concept invocable. So I think from the basic idea, maybe the function comes first, but once you start writing that, you pause and write the concept and then figure out that that you have the tests in place and then write the function, seeing that it works as expected. I hope this does answer your question. And the next one is, on the examples you showed now, most of the requirements were nothing more than each statement of your function can be called. Does it mean at one point that the standard will say, when no requirements are here, each statement of your template function will be an implicit requirement? Oh, that's an interesting idea. Well, despite that I'm in the committee, it's very hard to say what the future will be. I don't think so. And thanks for noticing this pattern. I didn't see it before. I think that's an artifact of coming with slide code. So with an example that fits on the slide and that's readable and digestible for the audience in time. It may be good if you achieve the same thing in a real world code base, such that every line comes with the requirement that's checked, but that may also be too much. So I think the idea is good. Whether it's achievable all the time is a different question. And this is not a point I did want to make, but I agree. This is what I showed. So, and then the next question for slide number 19. Thanks for using the slide number. So let's see what's on slide number 19. That's this one. Are you sure that static assert, which stood invocable of T, did not do the job for C++17? The static assert will do the job. The difference is the static assert, I don't know where you would put it, but somewhere after line number 2 and before line number 6. So inside the body of do locked. And by that, users have to look into the function to see which the requirements of this do locked function. And what I'm mainly saying here with the concept as the parameter, and it doesn't matter whether it's in the template head as a type constraint or here in the placeholder type constraining the placeholder type, it's not a function signature. It appears if you use the IDE of your choice and you see the function, it's documentation, and it's not hidden inside the implementation of do locked. So you can achieve the, oh, you shouldn't use it with that type situation in C++17, but that's too late. I want users to have a way to notice this up front and only have the compiler jump in if they violate it because for some reason they, I don't know, didn't understand it, didn't saw it, ignored it, whatever. Okay, but the static assert inside the do locked function, that's too late in my experience. All right, and by that, I think we are over the time. As I said, I will move over to the table. We have, I don't know, 5 or a little bit more minutes before I have to head to the next table for the book. But I'm happy to meet you there and see you there and talk to you for the first time then.
Yeah, and thank you again for your talk. And we'll see you at the question and answer table.
My
Thank
pleasure.
you for listening.
Bye-bye.
And bye.